I start a little bit. So it's a great pleasure to have Charles Adams around here in Singapore. In fact, we met approximately
22 years ago.
Shortly after the universe became transparent, I guess. So Charles did his PhD, I guess, in Strathclyde. That's like what I could trace back. Working on lasers at that time, designing lasers. And those of you who work in experiments or AMO experiments may have had a look at one of these lasers, coherent cells, this NBR 110 or something like that. So that's the gentleman who sort of like designed that laser and built it, and now that's sort of sold. He then moved for one postdoc to Condensed, and that's where we met. We continued working on building a laser.
Yeah.
And then switched more to atom optics as well to use that laser and apply this laser for a particular experiment. He then moved on to work with Steve Chu, Nobel laureate and ex-minister of, what is it?
Energy.
Secretary of Energy or something like that. Before he then moved back to UK in '95 or something like that, and set up his own shop in Durham, and he provided us with a map here. And I guess what I also should say, apart from him working on Rydberg atoms for quite some time, the main topic of this talk, I guess, Charles received a prestigious award from the Institute of Physics, that's the Physical Society in UK, just last year, on that work on Rydberg atoms. Something prize? Like
Thomson Medal.
Thomson Prize?
Yeah.
Thomson Prize.
After J.J. Thomson.
J.J. Thomson?
Yeah.
And I guess if you want to learn more about Charles or his work in Durham, just visit his webpage. You can also find lots of very nice pictures for what Charles does there. But without further delays, please go ahead.
Okay, thanks very much for the introduction. And it's a great honor for me to be here, to be invited here. My first time in Singapore, and it's great to see the wonderful work going on here. So I felt there was a real creative dynamic in what I've seen, and some real originality compared to all the old groups in Europe that are doing the same old stuff. So I mean, you're doing some great stuff here, and it's really nice to see that going on. All right, so I thought I'd just mention we do have a Rydberg conference in Durham, which unfortunately is the same week as your ICOLS. But I mean, if you're not going to ICOLS and you're interested in Rydberg, then you'd be very welcome. Okay, so I gave the title as Dipole QED, which may not sort of ring a bell to you because it's a sort of term that I've made up to some extent. So I'll have to explain to you what that is. It was very nice to see you made a nice poster for me, I like this picture. So what I'm going to do in the talk is first explain what this dipolar QED is, and then I'm going to talk about 4 experiments if I get time. So this is going to be quite demanding in the time available, so if we only get as far as 3, then I'll sort of shoot through the last one. But the main point is really to get an idea of what the physics is behind this, and then to look at some systems or examples, both applied and fundamental, where we see this type of physics. And I think it's a very interesting and expanding area of physics that's going to grow and grow in the future in many different directions. Okay, so let's begin with this now. So let's talk in very simple terms about what a dipole is. So if I have an atom, as you all know, there is no permanent dipole moment. But if I apply a field, then I can induce a dipole, and I get an oscillatory dipole. And this is associated with some transition between 2 states, usually. Now, what that dipole is obviously an oscillating charge distribution, and it damps, but in a quantum way, we think about this as a coupling to the vacuum. So this radiation is a coupling into the vacuum modes. And this coupling constant is the spontaneous decay rate, and we write it in this term in terms of a dipole moment. And then we can express it in this form where it depends on the transition wavelength and the cube of the transition wavelength. And you'll see why I write it in that form in a moment. So what we can think about this gamma, that we can think about this dipole, and it can exchange energy with the vacuum, exchange contour with the vacuum. And this coupling constant or rate of this energy exchange is given by this spontaneous decay rate gamma, and this depends on the transition wavelength. So that's what we know about dipoles coupling to the vacuum. Now, what do we like to do in quantum physics? Well, we're not happy with what the nature gives us, so we like to change it. So the first thing we do is let's change the environment of our dipole. And people have been doing this for many years, and this is the field known as cavity QED. So we changed the boundary condition, so rather than having all the free space modes, we now restrict the number of modes that my dipole can couple to, and we do this with a cavity by using high finesse, high reflectivity mirrors, such that it can only decay into particular modes, and this modifies this coupling constant. And now, if we go into this so-called strong coupling regime, where the coupling to the cavity is much stronger than the coupling to the vacuum, so we arrange that basically my dipole can only really exchange energy with the cavity now, then I can talk about excitation exchange with the cavity at some rate, which is usually given this symbol G. So this is a way of, and then we're very happy when we do this, because now we've controlled our quantum system. Rather than it decaying randomly into the environment, we know where the excitation's gone. It's gone into the cavity, and then it can come back again. And so we now have a nice coherent system, a closed coherent system that theorists and experimentalists try to emulate as well as they can. Okay, so now we'll go from this cavity QED to dipolar QED, or from C to D QED. So you can see that logically, if we start with cQED, the next thing to do is dQED. So maybe one of you wants to invent eQED, and that will be the future. Okay, so let's look at an analogy here. So we have now this dipole in a cavity, and it's basically a dipole with mirrors either side. And what happens if I look in a mirror, and there's another mirror behind me? I see these multiple reflections. And this was the best picture I could find on the internet, because it's nice because you see how each image is inverted. So basically the sign is changed each time I see a reflection. So what it looks like is an infinite chain of dipoles and image dipoles that each time are successively up and down, like a sort of antiferromagnet, if you like, in a spin picture. So now I've got this infinite chain of dipoles and image dipoles, and you could guess, if I replace these images now by real dipoles, you might guess, well, I get exactly the same physics, and that you would be right, that if we did that, so if I take real dipoles and I make a linear chain of dipoles and I put them inverted like this, then I get exactly the same physics as in cavity QED. So this is the dipolar QED equivalent of the cavity QED. I replace the single dipole and its line of images by real dipoles in an infinite chain. And just to show you that we get the same physics, here's a plot, a calculation of the line width. So this is essentially the coupling to the vacuum or to the rest of the world as a function of the separation of these dipoles, or the separation of the mirrors. And this dotted line is the cavity QED case, and these lines are the dipolar QED case as we add more and more dipoles. So for 2, you see it's still like a wave, really. And then as we add more and more, it gets closer and closer. So up to 50, it still hasn't got there, but you see it's approaching this cavity QED line. So this shows us a very nice analogy between the cavity QED case and an infinite line of dipoles, which we're going to call the dipolar QED case. And now we get to the difference. So now there's a fundamental difference, and it also tells us why dipolar QED is much harder, because here all we have to do is get one atom and stick it in a cavity. Here we have to get n atoms or n dipoles and arrange them exactly. We have to stick everyone in the right place for this to work. And as all the experimentalists will know, this is reasonably hard to do, especially when we want to get up to 50 in a line or something like that. But this system is also interesting because it's much richer. So here we really only have one dipole, and all the images have to do exactly the same thing. So whatever this master dipole does, everybody copies. But in this system now, everyone is independent. So we can address them all differently. We can initialize them all differently. And in fact, we don't need to put them in a line anymore. We can put them in any kind of system. So this system of dipolar QED is much richer than cavity QED. So we have a many-body system because they can all behave independently. And we also have this freedom of geometry to arrange it in any two-dimensional and three-dimensional structures. So it's much richer, but this richness also makes it much more challenging, both experimentally and theoretically. When we get into this quantum many-body physics, it's very hard to describe large numbers of interacting dipoles in this system. But that we like, because we like challenges to some extent. Okay, so here I've just got the sort of mapping between these two systems. So in going from C to D QED, we go from this system where we're looking at excitation exchange or photon exchange with a cavity. And we can define this strong coupling regime where basically exchanges more with the cavity than with the vacuum. And now we can define what we mean by dipolar QED, where we say that basically the effect of neighboring dipoles, we've modified our environment by adding neighboring dipoles. And to be in a strong coupling regime for this dipolar QED, we want the effect of these neighboring dipoles to dominate over the coupling to the vacuum. So we'll say that dipolar QED is when we see an effect where the neighboring dipoles dominates the interaction with the field, with the light atom interactions. And here we have this exchange, excitation exchange or photon exchange with a neighbor. And now we can ask, when do we get into this strong coupling regime? Well, the clue was in, if we go back to our spontaneous decay rate, it went as 1 over the wavelength cubed. And what we need now is to have an excitation of virtual photons or a dipole-dipole interaction that's larger than this. So rather than my photon going out into the vacuum, we want it to go to this neighboring dipole instead. And that rate is given by the dipole-dipole interaction. So this rate of virtual photon hopping between dipoles is given by the dipole-dipole interaction, which looks like this. So it's now dipole moment squared over the distance between the two dipoles cubed. So if I just compare these two expressions, they're almost the same, give or take a factor of 3 and 4. But basically, I can characterize this that as long as the separation of my dipoles R is less than lambda over 2 pi, then I'm going to be in this strong coupling regime for the dipoles, where the dipole-dipole interaction is stronger than the coupling to the vacuum. And of course, the more I satisfy this, the more strong coupling I am. So as long as I can put another dipole within a wavelength over 2 pi, then I'm in a regime where I'm more likely to exchange energy with that other dipole than I am to exchange energy with the vacuum. So this is the key point. So either writing it in this form, dipole-dipole interaction is larger than the spontaneous decay rate, or that the separation of my dipoles is less than the transition wavelength over 2 pi. I'm in this regime where dipole-dipole interactions dominate, and I'm going to see these dipolar QED effects and then exploit them in some system. So this is the condition we have to meet. And as we'll see, this is quite hard to meet for optical dipoles, because if you think about it, a transition is a few hundred nanometers. So this is typically separation of atoms that are less than 100 nanometers for optical transitions, and that's why these effects are maybe hard to see. But as with one of the secrets to doing this easily is to go to Rydberg atoms where we have transitions, wavelengths that are much longer, and then it's easy to satisfy this dipolar QED condition. Okay, so let's now look at an atom. So the systems I work with are atoms, simple atoms with just one electron. That's about the most I can cope with. It's already complicated enough. So here's the energy levels of an alkali atom. So here's the ground state, an S state, P state, D states, and so on. And you see these kind of nice sort of Rydberg series. And this is cesium, but I mean, basically they're all the same. And mostly what we concentrate on in atomic physics are ground state atoms, or sometimes we go here. And now there's an increasing trend to go up into Rydberg states because of the nice properties of Rydberg atoms. Now, any time when I make a transition here, so I have to, if I want to make an electric dipole transition, I need to change parity, so I need to change my L quantum number. So I go on some diagonals here, but each transition here is associated with a different wavelength and a different dipole moment. So I have a lot of possibilities here of transitions with different wavelengths and different strengths. So that's what we can start to think about exploiting. So here's a sort of diagram of just picking out some random transitions. So here's the usual optical one. In cesium, it's around between 800 and 900 nanometers. And this is an optical transition, and basically all these transitions down here in the near infrared. But then as I go higher up these ladders, basically the separation of the levels gets less, and I get transitions at a lower frequency. So up here I've got transitions in the terahertz regime, which is an interesting unexplored area. And then as I go up even higher, I get transitions in the microwave regime. And all these transitions are of interest now. And remember, for this dipolar QED, we're interested in satisfying this condition that R's got to be less than the transition wavelength over 2 pi. So for these microwave transitions, I just need to separate my dipoles by less than millimeters, and I'm in this dipolar QED regime. Whereas for these optical transitions, I need to separate them by an order or less than 100 nanometers. So this is hard, this is easy, but it turns out we can actually do both, and I'll show you experiments where we're in this regime for both these cases. Okay, so let's start talking about, these scalings are very useful to us about how we can look at different transitions and how the dipole moments and various properties scale. So if we want to go, for example, from a ground state to a highly excited state, the dipole moment gets smaller, which is going to be bad because this dipole-dipole interaction scales as the dipole moment, and that's getting smaller. But if we go up to these Rydberg states, we also get big dipole moments. So not only are we in this dipolar QED regime, but the dipole moments are extremely large, so we get extremely large interactions. So this is what we're going. So looking at Rydberg atoms is a very nice system to investigate these strong induced dipole-dipole interactions, which is what I'm going to sort of illustrate first. Okay, so that's the sort of introduction or part one about setting up what this dipolar QED is in a sort of a fundamental or global sense. So now let's look at some examples and some experiments which will hopefully sort of consolidate those ideas. So the first experiment I want to talk about is this sort of, I've talked a lot about excitation exchange. So in the cavity QED case, we talked about the photon going into the cavity and then back to the dipole or back to the atom. And now in the dipolar QED, it's an exchange of excitation between dipoles. So if this is an excited dipole in the excited state, it can transfer its excitation to this one, and then this one will be excited, and then it can transfer it back. So what I expect to see is an oscillation of these populations in the excited state as this excitation is transferred back and forth. And in a way, this is like a little nano cavity with just two dipoles or two atoms that are throwing a photon, virtual photon back and forth. So there's an excitation exchange. And as long as we're in this regime where the dipole-dipole interaction is stronger than the coupling to the vacuum, then we should be able to see this excitation go back and forth. And the fidelity will depend upon this ratio. So the larger we can make the dipole-dipole interaction relative to a coupling to the vacuum, the more times we can transfer this photon before it's going to come out into the system. So in order to observe this, we need the separation to be less than lambda over 2 pi. And so we're going to choose a long transition wavelength. We're going to choose a transition in the microwave regime between two Rydberg states. So by going high up to these excited states, we can get very large transition wavelengths in the sort of centimeter regime. And then it's easy to be in this regime where we've got very strong dipole-dipole interactions relative to any other couplings in my system. So what we'd like to do is take two Rydberg atoms. Now the experiment that we did on this, so this wasn't the first experiment that we did, but it's an experiment that I've been involved in quite recently, and for me it's a sort of real nice educational, pedagogical experiment to illustrate these ideas. And I was lucky enough to spend some sabbatical time last year at the Institute d'Optique with Antoine Brouet's group, so these are the guys in that group. And the reason why they're the perfect group to collaborate with is because they have very nice similar techniques to Christian here, where they have these optical tweezers and they can trap individual atoms. So they have experiments now where they can trap a few atoms, so they use a spatial light modulator to make multiple traps or multiple tweezers. So if you want to find someone who say, I want to take two Rydberg atoms, then these are the sort of people to go to, because they can load their trap with two atoms at any positions with any separation R, and then they can excite them to a Rydberg state. So that was the experiment that we set out to do. So the excitation of the Rydberg state we used was, it's not that important, but basically it's a pretty high Rydberg state. So it's n equals 62, and it's a D state, and that's not very important either. But what we're going to do is basically define our two states. So our two-level system is between the 62D state and a 63P state. And the transition frequency between these two states is 9.1 gigahertz. So this is a photon that's got an order of a centimeter or transition wavelength. So as long as I put my atoms less than a centimeter apart, then I'm going to be in this regime where the dipole-dipole interaction dominates. So what we're going to do is create this pair and then put one of them in this up state, which is like our excited state, and one in the down state, and then watch this microwave photon, this 9.1 gigahertz photon, hop back and forth. And that's what this dipole-dipole physics tells us should happen. So first of all, just to show that you can do nice stuff in this Rydberg manifold before you lose your atoms, we just want to see that we can drive this transition. So this is, if you like, a qubit where our 0 and 1 states are these two Rydberg states now. And this is very similar in a sense to the Rydberg qubits that Serge Haroche uses, but he usually just has one atom in a cavity rather than having two atoms that are interacting in free space. So this just shows we can drive nice Rabi oscillations, and basically you can go on almost forever with very high fidelity. And basically the limitation here is just on your detection efficiency. There's no dephasing of the... So it's a very nice sort of two-level system to work with in this system. And now this shows the transfer of excitation or virtual photon hopping that we wanted to observe. So initially what we do is we prepare one of the atoms in the up state, so with the excitation, and the other one in the down state. And then we just measure the probabilities of these ones and zeros as a function of time. And so over time, you can see this basically, the excitation goes from this left atom to the right atom and then back again. And you see it throws this photon back and forth about 6 times. So if I go to the next slide, you see. So basically, as we're going down here, the photon hops to the other atom, and then it hops back again to this one, and so on. So this photon is hopping back and forth. So you can see why I talked about this as a little nano cavity. I've got 2 atoms, and there's a virtual photon hopping back and forth between them, and that can happen. So it's actually quite a high finesse two-atom cavity. And if we just look at that, go back to this analogy now with cavity QED. So here's a plot from Serge Haroche's work where he sees excitation exchange with a cavity. So you put your excitation in your atom, and then it goes into the cavity and then back into the atom. This is now the same thing, but the excitation is exchanged between 2 atoms rather than with a cavity. So this really illustrates very nicely how I go from C to dQED, and the physics is sort of similar. So now that we've seen that this works, we can start to make the system more complicated. So here we have 2 atoms, and obviously we can add more. And that's the first thing that we tried to do in this Paris experiment, is not to only have 2, but to add a third one. And in principle, we can add more, and we can make it 2-dimensional, and it gets more and more exotic and rich and more difficult to describe experimentally. So let's just take the first step slowly of adding one more atom. So we can have more than one neighbor here. Now this just shows some of the things they can do in this. So I'm really advertising Antoine's work here, some of the things they can do. So using their spatial light modulator, they can create all sorts of patterns and arrays, and you can start to think about building up 2-dimensional arrays of atoms and then watching these excitations hop around in the system. So it's really a very nice system to play around with. And what we did so far was only really look at free. So it's not gone very far yet, but the first thing you want to do is free and see if you can look at this. So we looked at this excitation transfer in a spin chain of free Rydberg atoms, and this just appeared actually last month in PRL. So let me show you the results for this free atom case. So these plots over here are the theory, and then this is the experimental result. So let me just explain this through to you. So basically what we're doing now is at one end of the chain, we're creating this as spin up. So this one on the left has the excitation, and then it goes through the one in the middle, and then it ends up in the one on the right, and then it comes back again. And you see, you only get 50% probability for it to be in the middle, because basically it's distributed between the ends as it passes through. Now this would be the result that you get if there are only nearest neighbor interactions. But remember, this dipole-dipole interaction goes as 1 over r cubed. So actually the ends of the chain, this is a long-range type of interaction, so the ends of the chain are already talking to one another. And that turns out to be something that a lot of people don't have in their sort of if they want to build quantum simulators, they have nearest neighbor, but not necessarily next nearest neighbor interactions. So this system's maybe nice or maybe bad, depending on what you want, but you certainly have next nearest neighbor interactions. So if you add in the fact that the one on the end is talking to the one on the 2 ends are talking to each other 1/8 of the frequency, because it's 1 over 2 times the distance cubed. So now you've got this beating effect where you've got a 1/8 oscillation plus this normal oscillation, and so you get this beating. So you get this sort of revival in the probability. So this is what you would expect if the world was perfect and there was no bad experimental uncertainties. And then this is what we see in the experiment. So you see that there is evidence of this revival here. So you see a decay and then a revival. You can see it in this one. And you see the other one's very nice, but you see that over a relatively short time, so this is a few microseconds, the whole thing sort of dephases and gets bad. And this just actually shows how hard it is to do this type of experiment, because the experiment that they have in Paris is very, very nice and close to sort of ideal in that you can really put these atoms as exactly where you want. So where does this dephasing come from? Well, it really comes from the motion. So even though these are cold atoms and they're essentially fairly well localized, they're not localized well enough to make this happen with very... So when you include the finite spread of the wave packet of the atoms and their finite motion, then you get these theory curves which exactly fit the data. So the experimental imperfections come from the finite temperature, and even if you cool to the ground state of the potential, it's still not perfect because of the finite size of the wave packet. So it's very hard to do this stuff unless you really place your atoms as delta functions in space. They always got this finite spread. So that's interesting. But still, I think this is not too bad as quantum simulators go. I think this Rydberg one of this excitation hopping between excited Rydberg atoms is actually very nice and very competitive between what other people do. So as I mentioned, there's lots of people building quantum simulators now based on atoms, where they only have nearest neighbor interactions, ions, where basically it's difficult to go beyond 1D. Polar molecules, you can go 2D, but they have a very small coupling. And Rydberg's where we have an enormous coupling, but you can't keep the thing for very long. So basically everyone's in a sort of similar position in terms of figure of merits, but I think it's basically a very attractive system in which to investigate these model spin systems and do kind of quantum simulation. So that's an interesting direction for this sort of field, one direction for this field of dipolar QED. All right, so now I want to change track a bit and go on to my second experiment, and this is completely different, and it's another extreme really of the behavior. So what we talked about so far was looking at transitions between Rydberg states in the microwave regime. So we have these very long transition wavelengths. Now what I'd like to ask is, can we see any kind of evidence of these dipolar effects on the optical where we have to put our atoms less than 100 nanometers apart? And the answer is yes, but it's a sort of funny system. So firstly, the question is how to get into this regime where I'm less than 100 nanometers apart. And it turns out that that's quite hard for cold atoms or even for BEC. So it's very hard to reach densities. These are densities above 10 to the 15 per cubic centimeter. So this is very hard to reach with ultra-cold atoms. But if you go to hot atoms in a thermal vapor, it's easy to achieve these kind of densities. You can get to 10 to the 17. So you can put atoms 10 nanometers apart. But then it's really bad system. You know, you've got all these thermal motion, and you think, oh, it's going to be really terrible. We're not going to see any evidence of a nice dipolar QED effects. And it's very many-body. We've got a random distribution of atoms, and so we got this excitation exchange happening in some kind of random way. And I guess well, my first response, or anyone's response, would be, well, complexity, it's a mess, and I don't want to touch it. But let's have a go and see what we can see and see if there's any emergence from the mess. So this is what sometimes you can make many body systems are kind of a mess, but you see these nice emergent properties coming out. So what we want to do then is prepare a system of hot, dense atoms where the separation is very small. So we have atoms that are separated by of order tens of nanometers. Now, this is a very dense vapor, and if you go close to resonance, it's extremely optically fixed, so the light doesn't even get in, and it certainly doesn't get out again. So what can we do? So one way is to study this in a very, very thin layer. And there's this group in Armenia, led by David Sarkissian, who can make these nanocells where they can confine atoms between two plates, super polished plates. And the width of this atomic layer can be as small as 30 nanometers. So here you see these nice Newton rings, which tells you the thickness. So in the center here, it's about 30 nanometers, and then it gets gradually wider out to about 2 microns down here. And then you heat this thing up to about 300 degrees C or so it's 600 Kelvin. And then you get a very dense vapor, either cesium or rubidium, and you can still get transmission through this vapor. So you can still see transmission, and you can measure the spectrum of light, either fluorescence or transmission spectra of light in this atomic vapor in this very dense regime. So that's why we like it, because we can get light in and out, and you're not studying multiple scattering. You're basically studying the transmission properties or the optical response of these atoms in this very dense regime where they're within this sort of strong coupling regime of dipolar QED. So this just shows some sort of spectra that we might get, and we can fit these. We have nice models now where we can fit these spectra and we can extract a lot of information. This paper is actually about atom surface effects, but we can also study I'm going to show you in a moment is how we study the dipole-dipole interaction in this system. Okay, so here's the result. So what you see in this system are level shifts. So one thing you can measure line asymmetries, and you can measure line broadening, and you can also measure level shifts. So we have a model that fits everything, and what we extract from that model, from the spectra, is the line shifts. And then what you find is that as a function of the thickness of the layer, so we measure it at different thicknesses here, you actually get a very nice curve that looks like a sinc function. So this is fitting an awful lot of data, actually. It took a few months. It doesn't look hard, but it took a few months to gather all this data. And then we fitted all the data, and you see it fits pretty nice on this sinc function. And it turns out there's a theory for this that was done more than 40 years ago now by Rydberg and Manasa, Hartman and Mansa, reported in this physics reports paper. And basically the model says that you get basically a shift at zero thickness that's known as the Lorentz shift, and then you get a correction that's dependent on the length. And basically the idea is here that the laser's propagating through the medium and inducing dipoles, and then those dipoles produce a secondary field that can propagate either forwards or backwards, and then that field then goes back and interacts with the other dipole. So what you get is a term that depends on 2 times the wave vector times the distance, because it has to go there and back for a dipole-dipole interaction. So this fits. So here's the sinc function curve that fits very nicely to our data. Now this term is known as, so that in their paper they called it the cooperative Lamb shift. So we also called it cooperative Lamb shift. It turns out this name is controversial because some people get upset about the different usages of the word cooperative or collective. So there's a constant debate about that. So I just call it that. So I try not to enter into that debate, and so I just like co-Lamb shift. But it turns out that this effect is far more interesting than I think we realized at first, and it's actually stimulated a lot of new theoretical work, and I think it's a topic that we're still working on. And it shows us in a sense that by doing very simple physics, so this is just spectroscopy on a hot vapor in a thin layer, you can actually start to raise some fundamental questions. And that's what I find so exciting about this, that I don't have to build some million-pound apparatus. I just need to basically do careful measurements on a very simple system. So if we think about it, if it is a cooperative Lamb shift, why was it called that? Well, it's a sort of ensemble analog of the Lamb shift. So I told you with the Rydbergs, and we saw it happen in real time, in a sense, that this virtual photon exchange due to the dipole-dipole interactions. And this is exactly the same thing now. It's just in the optical regime, and it's a bit more sort of messy because there's an ensemble average and everything, so we get a shift. But it's basically exactly that analog of virtual photon exchange between atoms that gives rise to this effect. And it's actually also in a sense, it's the sort of real part that's associated with the phenomenon of super-radiance. So in the imaginary part, you get a super-radiant effect, and in the real part, you get a shift. So just like in the Lamb shift, where you get both these sort of terms. Okay, so how can we sort of take this further? So I've talked about quantum simulation. So this is a kind of analog simulator. So I certainly wouldn't call it a quantum simulator. And just to sort of show you some of the theoretical work that's been stimulated, here's a paper by Yavanin and Rushtakoshki that some of you may know. And I think it doesn't show up so well. I've blocked out most of there's some other text here, but that's the boring bit. So what it says, so this paper is called Strong Correlations in Light Propagation Beyond the Mean Field Theory of Optics. So this is I think it's an interesting topic because there's actually still difficulties about trying to derive Maxwell's equations in a medium when you're sort of close to resonance. And I hadn't realized that was a great difficulty that we still have to overcome after 150 years or so. But they say basically there's a failure of conventional optics when you have a situation where the atoms are spaced less than lambda over 2 pi. So in this regime of dipolar QED, we don't really have a good theory for optics, for mean field optics. And And so they tried to develop a theory that's based on discrete dipoles, and they say, well, basically it gets really hard, and numerical effort starts getting substantial by the time we have a few thousand atoms, which is exactly what we have, is a few thousand atoms. So in a way, when people are struggling with their computers to try and model these systems, what you need is an experiment that gives them some guidance. So I think it's very important that we continue these experiments in order to compare with these models and see if we can get some new insight into how to expand beyond these sort of mean field theories of optics in a media. So I think it's interesting in that sense. Okay, so that's my first 2 experiments done. So I think I'm doing reasonably well, actually. So we're now on to the third topic, which is maybe the one that's had the biggest impact, because things start getting real. We've talked about microwave dipoles and virtual photons hopping. Now we've talked about optical dipoles and virtual photons hopping and how those are going in sort of different directions of quantum and analog simulators. And now let's talk about what happens when we couple the 2 together. So things get really interesting and powerful when we sort of couple optical transitions to Rydberg states in such that we couple these nice properties of being in the sort of near field of these dipoles to the optical transition. And it turns out by doing this, we can make a very strongly nonlinear medium that's actually got a nonlinearity at the single photon level. So if you want to do single photon nonlinear optics, you could build a cavity, or you can just shine some lasers that couple to Rydberg states, and it does it all for you in a nice, simple way. So let's have a look at how we might sort of go about this. So in terms of the level scheme that I showed you on the previous page, maybe I should just go back to that just to point out. So the general idea is that we have an optical transition, and then we couple this to a Rydberg state using another laser. So it's blue, actually, for most atoms, blue or green. So I've shown it as a blue line here. So we have this coupling here. And some of you may recognize it. So we basically have a 3-level system now and 2 lasers. And you might, if you're familiar with that, you might recognize this is a scenario that people use in electromagnetically induced transparency. So let's have a look at electromagnetically induced transparency. That's usually done in this more conventional way in these sort of lambda systems. So you basically have an optical transition, and then you couple this to another transition. And this creates dark states, and it makes my medium transparent. And there's some really cool stuff that you can do with this. You can modify the group index of your medium, and you can make slow light, and you can store light, and do all sorts of neat things. So if you want to read about that, you need the original papers go back to about 2000 by Fleischauer and Lukin on this idea of dark state polaritons in EIT. And the idea is that basically there's a one-to-one mapping between light and an excitation in my medium. So if I have this 3-level system and I come into my medium with a pulse on this red line here, so I got this red pulse in the light, and then I lower the intensity of this coupling field, then basically I can slow down this red pulse here. In fact, I can stop it. So you see that happening here. As we get into the medium, it slows down, and it's transferred into this excitation in the medium. And then as we turn the blue light back on, it's released and read out again. So this is the idea of light storage in a medium that lots of people have been doing experiments on, and now they do it also in solid state systems in various different ways. So this is a very nice idea that I've got this one-to-one mapping between a light field and an excitation in my medium, and then I can store it for a while and then read it out sometime later. Now when we started so we were interested in this EIT business, but it sort of looked a bit discouraging, because if you read the big review, which is really nice, it said, we will be most concerned with the lambda configuration, since the ladder, which is when we put this up here, is a limited utility. So I guess if I had taken that too seriously, I wouldn't have even started. But fortunately, I hadn't read it at the time. So anyway, we thought, okay, let's try and do this EIT business to highly excited Rydberg states. And we thought it probably wasn't going to work, because if it did work, then lots of people would have done it already. But fortunately, it worked really well. So it worked surprisingly well. It worked first time. So we were very happy. So what we did was sort of wrap out this lambda system into a ladder system and go to a highly excited Rydberg state. And this shows just one of our sort of these Rydberg resonances in one of our first experiments way back now in 2006. So that's when we got started in this whole business. And even way back then, in 2006, we actually measured Rydberg spectra all the way from 25 to 125, and that was in a thermal vapor cell. So it actually worked surprisingly well, and we could go to reasonably high Rydberg states with principal quantum numbers up to 125. And we just got bored then because we wanted to go for dinner. So probably we could have gone higher than that. So but that anyway was as far as we get. We never really tried to go higher because basically at around 100 you can already do all the nice physics. So now the idea then is that we can sort of store excitations in these Rydberg states and do interesting things. And then when it's an excited Rydberg atom, we know it's going to have these strong dipole-dipole interactions that we've already seen. So if we've got this nice one-to-one mapping between light or photons and Rydberg excitations, we can now make our photons interact via the dipole-dipole interaction. So that's the basic idea of what we're going to try and do. Now, it took us a while to get this working from those first experiments, so there was a little bit more to do. So firstly, you have to go to cold atoms, and because you don't want motion messing up this storage of the light pulse. So basically, if the atoms move, it causes a dephasing, and then the light doesn't come out in the direction that you put it in anymore. So you go to cold atoms, and you need a fairly high density. So what we do is we store atoms in an optical dipole trap, and it's quite a small trap, so it's only 2 microns across by about 15 microns long. And then coaxially we send through our probe light and also the Rydberg excitation light. And then we go through this storage sequence where we try and basically store photons as Rydberg excitations, and then we read them out, and then we do measure photon correlations using one of these Hambry-Brown Twiss type interferometers. So we look for coincidences, and then we can see if we've modified the photon statistics of the field that we put in. Now, when you work with Rydberg atoms, a lot of the challenges, they're very sensitive to electric fields and things like that. So that was the biggest problem that we had to overcome, as we had to build this little sort of gizmo with all these electric field cancellations, and we had to coat our lenses with special ITO coatings to stop all stray fields and things like that. So that's why it sort of took us quite a long time from the preliminary experiments to get all this stuff to work. Okay, so here's the experimental sequence where we try to store photons in a Rydberg state. So this is sort of Rydberg quantum, short-lived Rydberg quantum memory. But the point is that because the Rydberg interactions have such strong interactions, we don't need to store the photons for very long in order for something interesting to happen. So we go through this sort of storage sequence where we've got a pulse of red light on this sort of strong optical transition. And initially we have this control light on, and then we turn it off. So this is when we transfer this light pulse into an excitation, so it gets turned off. And then we turn it back on, and then we read out whatever we've stored. So first of all, we'll just see that this is the actual signal. So this is the light going off here. And then when we turn this control pulse back on, these dots here show that we get something out. So that shows that we were successful. We stored some light, and then it comes out again when we turn this back on. And if there are no atoms there, when we get no light out. So that's reassuring that the experiment is working. So now that we've got something stored in this Rydberg state, and it's now a Rydberg excitation, but it's shared over all the atoms, so we don't know which atom is excited. It's actually it's essentially a polariton or spin wave, where this excitation is shared amongst all the atoms in my dipole trap. And these phases are important because that's what determines the directionality of the readout. So I've stored some excitation and with this nicely arranged phases so that I can then read it out in the same direction that I put it in. And then we want to do something interesting to this stored excitation. And now we couple it with the microwave field. So we talked about microwave fields earlier, about how they're very nice because I can drive transitions. So I should be able to take this stored Rydberg excitation and do Rabi oscillations on it, and then see that it goes to another state. And then if I try to read it out, it won't be there anymore. But then when it comes back, I can read it out again. So we'll try and drive some Rabi oscillations. Okay, but the first thing I want to show you is that there's an interesting effect about this medium and what it can store. Because there's a process known as blockade. So blockade means that if I've excited a Rydberg excitation, then because of these dipole-dipole interactions, I shift the energy levels of nearby states off resonance, and I can't no longer excite to another atom nearby to a Rydberg state. So that means I can only store one Rydberg excitation within a given volume that's given by this blockade radius that depends on these interactions. So if I have a certain volume of my cloud, I can only fit in a given number of excitations, and then it's so my memory is blockaded. There's an upper bound to the amount of photons I can store in there. And that's what we see if we just basically do storage. So if we just do storage and then we look at coincidence counts, we see that when we store photons, for these photons that are, so for the pulses that are correlated against themselves at 0 time delay, then we see that we can't get classical light. We get non-classical light, so the light becomes anti-bunched. So there's a suppression of high photon storage numbers. But you see that it doesn't go all the way to 0 because our cloud can support more than one excitation. So it's not so small that it only supports one. In our case, we can support about 3 excitations, and this coincidence is suppressed by about a third, roughly, which is what we'd expect. So we're limited to store 3 excitations in our medium by these interactions effects. And now we can start to drive Rabi oscillations. So we start to, and then this is so what we're going to show now is these Rabi oscillations as a function of increasing microwave power. So as I crank up my microwaves, I'm going to basically drive more oscillations in a given time, and I should see nice Rabi oscillations. So this is where we start. And then this is the Rabi oscillations that I get. So you see basically the thing goes away, and then it comes back, goes away, comes back, goes away, comes back. You see it doesn't come all the way back. And the reason why it doesn't come all the way back is because basically we're changing now the interactions between these polaritons, and we dephase them. So now some of the stored photons come out in different directions. So we don't recover all of them. And in principle, what we should be able to recover is at least 1, because when we're down to 1, it can't dephase against anything anymore. So this process of driving the Rabi oscillations makes our system more single photon-like, because we basically dephase higher photon numbers more rapidly than we do single photons. So if I now do a G2 at this point, you see it's gone down. So what we've now done is processed optical photon statistics with a microwave field. So that's sort of a nice thing, because it's a sort of microwave to optical interface that works at almost a single, well, it works at a single photon level in the optical. And so this is a very nice tool that I have a control parameter where I can control the photon statistics of my light field. So now you can start thinking, can I make this better? So this is not ideal because it's sort of lossy and I kick photons out. But can we sort of start to think about doing things better? So what we're now trying to do, and we haven't done yet, but we've built a new setup now, whereas instead of all the photons going through one channel and there being these Rydberg excitations basically arranged longitudinally, we now want to arrange them side by side, where I just get 1 here and 1 there. And we have 2 channels that are separated going in and out. So this looks very much a bit like a gate protocol now. So you can talk about this as being a target, that if I put a photon in here and create a Rydberg excitation, it's going to shift the energies and modify the medium for this second photon, my target photon. So I can use this controlled photon to induce a controlled phase shift on this one. Now what's tricky here is that basically propagation and interaction are all wound up together. And in fact, you can go back and find papers by clever people like Shapiro and Guillebanne-Cloche that say if you have very large single photon nonlinearities, Kerr nonlinearities, it doesn't help you to do quantum computing, because what happens is you just distort the wave packet in some horrible way. So the photons you don't get out don't look like the ones you put in, and then when you interfere them on a beam splitter afterwards, you don't get any high fidelity operations anymore. But this Rydberg blockade is not a Kerr nonlinearity, it's like an on-off switch. So either it happens or it doesn't happen. So this is nice because we can completely separate the propagation from the interaction. Basically, we completely map into this Rydberg manifold, and we've stored the thing, and then we can do a global phase, and then we can read out again, and we can separate these two. So we can get round these problems of Kerr nonlinearities. So in principle, you can build a very nice photonic phase gate using this, and that might be a vision. We're not really trying to build one on a chip like this, but it's nice to have a picture, show you what you could do if you do. So we're trying to build something like this now, but not on a chip at this stage, and see how well we can make it work. So that's the direction that we're going. Okay, so I'm now on to the last topic. So I think I've just about got time to cover it, which is good. So I want to talk about another Rydberg experiment now, where we go to, but now it's a bit different. So the theme is a bit different because we're going to look at sort of some many-body physics. And and again, it's about dipole-dipole interactions and light, but it's about the system more than the light now, in a sense, although we can now exploit this and to do interesting things with the light. And again, it's a very simple experiment where this time we take cesium atoms, but it could also work with rubidium atoms. Again, it's in a vapor cell, and then we just excite to a Rydberg state. And we happen to use this free photon excitation scheme, but that's not so important. The important thing is that we excite Rydbergs in this system, and then we look at what happens. And this was a surprise for us because we didn't expect this. So we started doing these experiments, and this is our vapor cell, and we shine in these free lasers. And the really nice thing about doing this free photon, and why we discovered it probably, was because all the photons that we use are infrared, so you don't see them with the naked eye. And then when you go in the lab and you look at your cell, and you see that your cell lights up as you hit the Rydberg transition, and it's a nice green color. And this is a decay from the Rydberg state down to a higher lying state that emits this nice visible green light. So when you first see that green light, you're really excited. In fact, the student phoned me up in my office saying, "You've got to come to the lab, the cell's going green." And so I came down, we looked at the green, we admired that for a while, and then we decided we wanted to go to higher density. And actually he did it really fast because he had this short cell set up that was in an oven, so this is higher density. So he just switched all the lasers across to that. And then I'd gone back to my office, just settling down for a nice coffee, and the phone goes, and he said, "You're not going to believe this, it's gone orange," he said. So I come down to the lab again, and I look, and indeed it's orange. So we were completely staggered at what the heck is going on here. How can it go from green to orange? So this is, and I think we're still very excited about this because, you know, we've been working on Rydberg atoms for sort of 8 years, and we never really, you don't see, it's like a lot of these modern quantum experiments. It's like you've got your computer and you program away, and then some data comes out, you fit the data, and you say, oh yes, that must fit the quantum physics. But you don't see anything with anything dramatic with the naked eye. Whereas here you can come and visit me in Durham, and we show you this, and you see it light up, and you think, wow, this is dipole physics happening, and I can see it, Rydberg physics happening with the naked eye. So we were very excited about this. It turns out this is a bistability. So it's a bistability or a phase transition. And it's a phase transition between a state of low Rydberg excitation and a state of high Rydberg excitation. And essentially it comes about because of the level shifts induced by the dipole-dipole interaction. And you can make a very simple model where you just look at excitation and you put in a level shift that depends on the amount of excited atoms you've got. And that's what you get here. So this is just a model where we basically say how many atoms are excited, and then I shift my line. As I excite more atoms, I shift it more. And basically you get a bistability in this model. So it's a nonlinear oscillator type of situation that the harder I push it, I change the frequency of the spring, and then you get this bistable behavior. And that's exactly what we see. So that's a very simple picture of what's going on. And then it changes color. So as I'm going along here, I'm sort of green, and then when I shoot up here, I go orange, and then I go down here. And you can really see that we can get even both at the same time. So here's the sort of green state at the bottom. And then you see it sort of spread through the medium here, and you get this phase boundary between these different zones. Now you could ask me, why is it red? So this is a complicated question about why does it change color? And we think this is a super-radiant cascade. So when we have many Rydberg atoms, then they can transfer very quickly to a lower lying states in the microwave and terahertz regime. So they then decay from lower lying excited states that of course have longer wavelengths, and so are more orange than this green here. So, but we haven't really, it's very hard to prove that you have a super-radiant cascade because there are so many levels involved that it's rather complicated. So we're still working on that, but it looks fairly we can look at spectra and we can see that that's really what's going on. So there's a very rapid sucking down of energy into states that are slightly lower, and then they emit at a longer wavelength, so it goes from green to orange. Now, this is interesting in the whole field of sort of condensed matter, many-body physics, because it's a critical phenomenon, it's a phase transition, and you can look at things like, well, we thought this was critical slowing down, but you can look at critical exponents at this switching point. So it turns out that when you try to switch the medium from green to orange, it doesn't happen instantaneously. So the system has to order itself in some way. And I understand this in terms of this sort of umbrella problem that people like to talk about in the Rydberg physics. So if you want, so creating a Rydberg atom is a bit like putting up an umbrella. I need space, right? Because it influences everybody in my environment. So if we all try to, if we're too dense and we all try to put our umbrella up, then there's going to be one poor guy, he can't get his umbrella up. And then it takes a bit of time for everybody to rearrange themselves so that everybody can get their umbrella up. And so that's what's happening here, that we need to find a configuration where this transition is allowed, and this takes a bit of time. And that's what's associated with this time constant here for the critical exponent. And there's now some theoretical work that this is my simple picture. There's now some theoretical work where they understand this in a bit more detail, and they get the same critical exponent that we said in terms of these sort of double well models and falling over hills. And it turns out there's some other interesting critical exponents we could look for in this system. So it's nice. We have, again, a very simple experiment, which is just shining lasers at a sort of hot gas, basically, and we can do some fairly fundamental sort of condensed matter-like physics or soft matter physics or whatever you like to call it. And just very recently we've been excited about this transition because we managed to drive this transition from green to orange using a terahertz source. So if you remember when I showed you all these level structures, there's a sort of zone in the middle where there's all these terahertz transitions. So if we go to high Rydberg states, we've got microwave transitions, and then in the middle we got terahertz. And we borrowed a terahertz source from Mike Tarber at Imperial College, who's doing molecule spectroscopy with it. So we borrowed his source, and 2 days later, we'd managed to make this medium switch between these two states using terahertz. So I think it's got possibly it could be something really interesting for applications, because there are very few ways of detecting terahertz, and there's certainly not many ways of doing terahertz imaging. So you can start to think about imaging terahertz fields, and the whole thing will just light up and give you green or orange depending on where the terahertz is. So it's nice that sort of some physics like this maybe can point towards some sort of applied things that could be useful. I don't know if it will be useful, but let's hope. All right, so that's brings me to the end. So my last slide is really sort of acknowledgements, because clearly I can't do all this stuff on my own, and I've got various staff colleagues that work with me, Ivan Hughes on these nanocells, and Kevin Weverill on the cesium and terahertz stuff, and Matt Jones works with me on the cold Rydberg quantum optics stuff, and then a whole series of postdocs and some superb PhD students, and also we need theorists to help us explain what we're seeing sometimes when it gets very complicated. So I think I'll finish there and leave a bit of time for questions, hopefully.
Thanks a lot, Charles, for the very exciting talk and conveying a little bit of the fascination you get as an experimentalist. And some of the theorists get a bit jealous, but yeah. I'm sure there are questions in yours. Please don't be shy.
Yeah.
In the experiment of the hot atoms with the thin cell,
yeah.
What is the role of the van der Waals interaction
with the surface? Yeah, so it depends on the regime we're in. So when there is a shift with the surface, but it only really kicks in at a sort of like about 100 nanometers or so. So if we want to measure the dipole-dipole interaction, we go with the slightly larger cell and higher density. But we can basically subtract it off. So we can basically fit all the data for different widths of cells and different density, and we can understand which is the van der Waals shift and which is the dipole-dipole shift, and we can separate them all just because we accumulate data over the whole parameter space.
In this experiment where you see that you have this super-radiance effect, so you would expect maybe super-radiance to be more along the
length
axis rather than isotropic, and it looks like isotropic because you can see it.
Well, the super-radiance is probably in the microwave and terahertz domain. So what happens is you come down, so you've got this, you're in a sort of high Rydberg state, and then you've got a transition in the microwave or terahertz regime to a lower Rydberg state, and then you decay from there. So what we see is a sort of secondary, we don't see the super-radiant transition directly. So we'd need a detector in the microwave or terahertz regime to see it.
So, when we maybe first, and then
I have a question in regard to the first experiment, this three spins.
Yeah.
And then you show this, when you have three spins, and then you have simulation, and then there's some revivals and everything. I was just curious, you simulate or goes to experiment for longer period, such that, because at the end of the experiment, seems everything almost decays off, but there could be, for some reason, even completely defect, they can still revival later on.
Yeah.
But I was wondering, you have done that experimentally with simulate.
No, we.
That's just a totally different.
So the limitation of the experiment is we can't do it for longer because basically what you trap the atom and then turn the trap off in order to do the experiment, because there's all these differential shifts from the trap. So because you can't trap the Rydberg atoms, you have to turn the trap off. So the time that you have is until the atom's fallen away, and then you want to recapture the atom to detect it afterwards. So the limitation is about sort of 10 microseconds, something like that, which is the maximum time that you can sort of let the atom go for and then recapture it again to detect which state it was in. But there could be, I mean, there are developments in the Rydberg field with people now starting to trap Rydberg atoms and also trap them using magic wavelengths where they can, you can drive transitions of trapped Rydberg atoms, but it adds some complexity.
So this is a theory perspective question. So some of us, I mean, here and also I see Thomas and Thomas Paul and Michael Klaskar are interested in historical correlated states of light and, and you know, being proposals using Rydberg atom for Wigner crystals or, and things like that. How do you see this from the experimentalist perspective? I mean, how far off are we? I mean,
I think we're pretty close. So, in a sense, what you want. So, what basically we've done is seen the single photon nonlinearity, and then what you want to see is a sort of propagation effect or storage effect, where it really then arranges itself, so that you see a sort of anti-bunching of the. And I think it's just a case of reaching a high enough optical depth in your sample. And I know the MIT group are working on that, and I think they're pretty close to having sort of at least first evidence of seeing some sort of the voltage group. Yeah. It hasn't been something that we've pushed for. But I think we're getting pretty close to being able to see essentially crystallization of photons in these media. Yeah. Yeah, we've got some. I didn't include them here just for time, but we do a spectrum, when it's in the green state, and we can see all the transitions that are getting excited. So basically, when we're in the green state, you see predominantly decay from the state you're exciting down to one of the p states, which is a green transition. So in our case, we're exciting like 20 n equals 26, and it decays all the way down to the 6p. But when we see the orange light, it's decaying from around 13. So what happens is there's this very rapid energy transfer, say from 26 to 13, which are these sort of terahertz transitions that I mentioned that we don't see, and then we see these orange transitions coming up.
So the green line and the orange line itself is like one spectral line?
Yeah, they're really individual lines. So we can assign all the lines. So we actually see lots of colors, but we can assign all the lines that we see in the spectra.
It seems to me that the orange light is connected to the ground states because you see it's spreading all over the cell.
But the spread. No, the spread is really the motion of the atoms. So it's something that we're trying to understand a little bit is the phase boundary, because what we've shown is when we look at this phase boundary as a function of detuning, we see that it basically becomes more sort of conical, or it changes shape depending on the detuning. So it's related to the motion and the lifetime of the atoms in that. So basically the atoms can move and then fluoresce. So we've been trying to understand that a little bit, but and we're getting closer to understanding what it is. But it's basically like how far can they move before the photon is emitted.
You see some kind of exponential shape here in that case?
Yeah, essentially I think it's an exponential. It's like the Gaussian. So there's a convolution. Yeah.
So I mean, you see these nice colorful short wavelength responses, I guess. Can you see something if you manipulate the terahertz or microwave transition that are necessary, or they're very fast? I mean, the wavelengths sound at least so that you could do maybe something with.
Oh, you mean to go very fast in the.
Yeah, or prohibit some of the terahertz transition. Is it possible that it can build mirrors or like boundary conditions this frequency.
Possibly, yeah. You mean to reflect terahertz or something?
Something like that, but
yeah.
you see a pattern in the cloud or something.
I think there are all sorts of possibilities because the terahertz transitions are so strong. So you can certainly think about. Like, I mean, there is some Doppler broadening in this medium, and so that's maybe not so ideal. But we're just beginning on the terahertz journey. So so I think all possibilities are sort of open there. But I think it's a great. So what we'd like to do is make a kind of source. So our dream was to make a sort of terahertz laser source. So a narrowband source out of this medium. So a laser or taser or something, and then have this detector and see that we can get that one to, and maybe it's even a super-radiant taser. But I don't know whether all that works. So that's something to start to begin to look at. But,
any other questions, comments? If not, maybe then we take the opportunity to thank again Charles for a nice talk.